This is part 3 of the series Limits, and in this part we're going to begin by working a couple of problems that use the epsilon delta definition of a limit. In this first problem we want to use the limit as x approaches 3 of 2x minus 5 equals 1 to find some delta such that f of x minus L, you can see that this is f of x, and this is L, the 1 is L. F of x minus L is less than 0.01. What this is giving us is the epsilon. So given an epsilon, we're looking for a delta when 0 is less than x minus 3, which is less than delta. So the easiest way to proceed with this thing is to see if we can somehow match this expression with this and find an expression x minus 3 somewhere in here that will give us our delta value over here. So we can notice that we can expand this piece, and we would end up having, let's do this over here on the right hand side, we'd end up having 2x minus 5 minus 1 is 2x minus 6, and the absolute value of that is less than 0.01, and we can pull out a 2 out of this. So this is 2, and x minus 3 is less than 0.01, and if we divide both sides by 2, and therefore x minus 3 is less than 0.005. So since this expression here is equivalent to this expression here, then I can choose, since x minus 3 and x minus 3 are equivalent, I can choose my delta as 0.005. So that's what I set my delta to. Alright, let's work one more problem. In this problem, we want to use the epsilon delta definition of a limit to prove that the limit as x approaches 2 of 3x minus 2 equals 4. Let's go ahead and start with the definition of the limit. We know that 0 is less than x minus c, which is less than delta, that if this is true, then the absolute value of f of x minus L has to be less than epsilon. So putting in our values here, we know 0 is less than x minus c, being 2, is less than delta, then f of x, which is 3x minus 2, minus L is 4, is less than epsilon. And if we work just like we did up here to simplify this, we know that 3x minus 6 is less than epsilon. Pull out a 3. Three times absolute value of x minus 2 is less than epsilon, and then divide by 3. Now, given that these two expressions are equivalent, we can say that our delta is equal to epsilon over 3. So our delta is any epsilon divided by 3. All right. Now let's go ahead and let's look to some properties of limits. So here's a set of properties for limits, and our given values are that a, b, and c are real numbers, so there's b, c, and the a value here are real numbers, and further that if we assume that the limit as x approaches c of f of x equals j, and the limit as x approaches c of g of x is k, these following properties will apply. Let's take a look at this first one. The limit of b as x approaches c equals b. Well, this is basically, if b is a real number, this would simply be something like y equals 2. And you know that the function y equals 2, let's say it's y equals 2, this is simply a horizontal line. So no matter what your x value is, this function is always going to equal 2, because this y value is 2 up here. So it's always going to equal 2. So the limit as x approaches c of y equals 2 is always 2. So whatever b is, that's the limit. Now the limit as x approaches c of x, this is the function y equals x, and y equals x is simply the line y equals x. And we can just do a direct substitution in here. We can take that c value, plug it in for x, and our limit is c. So that's all that's happening here. For this function, we're doing basically the same thing. We're just doing a direct substitution. If we have x squared or x to the third or x to the fifth, whatever it happens to be, we just plug the limit value c directly in. So if we wanted to find the limit as x approaches 2 of x to the n, it's simply 2 to the n, which is just c to the n. So in these three, we're just doing a straight direct substitution. Now in this limit, we see that the limit as x approaches c of some constant times the function equals the constant times the limit of the function. In essence, what we're doing is we're pulling out the constant from the function. For example, if we had the limit as x approaches 3 of 2 times x squared, this is the same as 2 times the limit as x approaches 3 of x squared. We just pulled out the constant out in front. We do a direct substitution. That's 3 squared, and so the limit is 3 squared times 2. In essence, all four of these now are straight direct substitutions. Looking at this one, we can evaluate this limit by simply saying that the limit of the sum or difference of the two functions is the sum of their limits. So if the limit as x approaches c of f of x is j, which we set up here, and the limit as x approaches c of g of x is k, which we set here, then we know that the limit of f of x plus g of x is j plus k, this limit plus this limit. And the same is true for the products. So the limit of a product of two functions is the product of their limits. Same thing is true for their quotients. The limit of the quotient of two functions is the quotient of their limits, assuming, of course, that the limit of the denominator isn't 0. And then the last one, that the limit of f of x is the limit of a function to a power is the limit to that same power. So we're just doing, in all of these, we're doing direct substitutions to find those limits. And that's assuming that a direct substitution works. But we're going to look at cases where we can't just directly substitute. When we try to put in these values, some of these properties are violated, so we're going to have to do some special work. These are basic properties that will allow you to make quick work of 80% of the limits you're going to encounter. But we're going to look at others that we're going to have to do some analysis on to solve in a special case. So let's take a look at evaluating some limits analytically. In this first problem, we want the limit as x approaches 2 of this polynomial. And we know if we wanted to write this out using each one of the individual properties, we know that this is the same as 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. And we know this limit is just 3, and this limit is just 4 times 2 squared. And we can add these two together. And if you notice, that's all we've really done by breaking this apart, is done a direct substitution into this polynomial of the limit value you see here. And so you can accomplish the same thing, but just by doing a direct substitution, you have to be conscious that you're not violating any fundamental mathematical properties by doing it. But in this case, we have 16 plus 3, which is 19. Let's go ahead and work this problem now. We have the limit as x approaches 1 of this rational function. Now, the only obstacle potentially to evaluating this by direct substitution is if the substitution makes this denominator 0. Well, since this is a positive value, this becomes a positive number, so it's not 0, so we're clear. So it's all we have to do is directly substitute the 1 in for x. So we have 1 squared plus 1 plus 2 over 1 plus 1, which gives us, on the numerator, 4 over 2, which is 2. So that's a fairly straightforward one. Now for the third one, again, the only obstacle here to a direct substitution would be if this c value made the radicand negative. Well, in this case, this x value would be 0, so we just have the square root of 4, so it's 0 squared plus 4, which is the square root of 4, which is simply 2. So the limit of this is 2. And here we have the same thing. If we direct substitute in here, we have 2 times 9, which is 18. This does not make this negative, and even if it did, it wouldn't matter because this is a cubic root. So this is the cube root, and cube roots can be negative. We can take the cube root of a negative number. So we're looking for the cube root of 18 minus 10, which is the cube root of 8, which is 2. So 4 pretty simple limits of just examples of implementing those properties, and fundamentally what it comes down to is direct substitution as your simplest course. So let's take a look at a few more. In this set, we're going to be looking at the limits of trigonometric functions. Now with trigonometric functions, we can almost always use direct substitution. We just have to be conscious of what's going on here. So let's take a look at this first one. The limit of tan x as x approaches 0. What we have, tangent is sine over cosine. So the limit as x approaches 0 of sine over cosine, for direct substitution, that would be the same as saying sine of 0 over cosine of 0. In case you don't recall, in the unit circle, we know the y value is sine, the x value is cosine. So at 0 degrees, the sine value is 0. And the cosine value is 1. So this becomes 0. All right, let's go ahead and look at this one. Now in this limit, we're doing direct substitution. We have pi times cosine of pi. Well, back to this, pi degrees is over here, so cosine of pi is -1, so it's pi times -1, which is -pi. So that's the limit as x approaches pi of x cos x. Now for the last one, this is equivalent to sine x squared. We know the limit as x approaches 0 of sine x is 0, so this is going to be 0 squared, which is simply 0. All right, let's go ahead and take a look at another set of limits, but we're going to do that beginning in the next part. So I will talk to you in the next part.